This project consisted of two parts. The first part was a straightforward test of the UART communication between the terminal and the board. If a character was typed on the terminal, it would either turn one of the onboard LEDs on or off, considering that it was one of the specified letters. A display message would also be sent to the terminal, letting you know which LED was on or off. As well, the onboard switches were initialized so that if either were pressed, all the LEDs would turn on or off. Again, a display message was sent to the terminal letting you know that all the LEDs were either on or off. We begin by initializing port F for pins 0 through 4. Then we initialize the ISR. We initialize this so that whenever the onboard buttons are pressed, an interrupt will occur and we can perform the code specified in the handler. In the handler, we check to see which button is pressed. We acknowledge the flag, turn the LEDs on or off and send the specified message to the serial terminal. The UART is initialized as was in Lab 4. We set the clock, initialize the baud rate, and set the pins. Then we create the busy wait function for the input and output character. The purpose of the main function is to set up what the UART will receive and transmit. We use a switch statement and if-else statements to turn the LEDs on and off and display the appropriate message to the serial terminal.
For Part 2, two separate project files were created for each respective TIVA board. For the first microcontroller, we need to set it up so that the first microcontroller can communicate with both a computer terminal and the second microcontroller. The second microcontroller needs to be set up to take in an analog value, convert it to digital, and communicate that value to the first microcontroller. In the first file, we will look at the initialization in port F.C file. The only GPIO set is on pin 2 so that the blue LED will be activated. Notice that it is necessary to enable it as an alternate function and enable analog functionality. This is because we are activating the PWM functionality. We then set up the necessary drivers for the PWM. The PWM is needed so that the LED can either brighten or dim, depending on the information received from the second microcontroller. Next, we look into the initialization of the UARTs. In the UART.c and UART.c files, we initialize the UART as we did in Lab 4 with minor adjustments for address for UART. In the main file, we initialize the functions as normal. The bulk of the functionality is in the SysTick handler. This is where we set it up so that the UART communication can occur between the microcontroller and both the serial terminal and second microcontroller. The value received from the second board, through UART1, is assigned to a variable. This value is then used to determine the PWM value assigned to the blue LED. This is how it is either dimmed or brightened. Simultaneously, we communicate this PWM value to be displayed on the serial terminal. We then prompt for a character to be entered on the serial terminal. If the value entered is an R, it will be communicated to the second board. Now let's look at the project files for the second TIVA board. We initialize the ADC on A9 or pin E4. If we look at this port F.C file, we initialize the port F to activate the LEDs and onboard switches. We then instantiate a handler on port F so that when it receives an interrupt, the button is pressed, the LEDs will turn off and a counter value will reset to 0. One UART is instantiated and, again, it follows the similar formatting as in Lab 4 with the adjustment made for UART1. In the main file, we initialize functions as normal. In the endless while loop, we are looking for a character received from the first microcontroller. If that character is R, We change the LED value to red and set the counter value to 1. We initialize the SysTick to set the sampling rate of the ADC. In the SysTick handler, we sample the analog value from the potentiometer and communicate it to the first microcontroller. Then, depending on the count value, we toggle the LED, or we retain the current LED value. Again, pressing the onboard switch will turn off the LED and reset the count value to 0 so that the data will not toggle. You will notice in the following demonstration video that a character has to be entered so that the ADC value is updated on the terminal and the LED value as well. This is due to the character input function not being written in a non-blocking fashion. Though data is transferring, we do not see it update on the screen until we exit the busy wait.